Hello and good afternoon and welcome to this talk about a problem you may have been facing. Otherwise, you probably wouldn't be here. And really nice to have all you here. I recognize some friendly faces here that I've been talking to throughout the conference. And it's been a really good conference so far. So let's wrap it up on a high level here. I'll try to do my best for you guys. So we're going to talk about security today, more specifically open source security, but in the context of the behaviors of the team and how you can reason between team and technology of your security alerts, more specifically. And looking at today's landscape of how security on your code base works, at least, is that you typically run it in your CI and in a continuous scanner. And you may be trying to shipping a new feature, or you may even have downtime in production and need to get this fix or patch to your application out as fast as possible. But there you go. Your pipeline is failing because your vulnerability test is screaming, oh no, you cannot merge this pull request. But it turns out to be a false positive, and in the end, your developers are experts at getting things down, meaning shutting down that pipeline. So, my name is Emil. I'm a spaghetti coder still. I founded The Bricked in 2018 with some friends, took some VC capital. We're based here in Malmö. 6 months ago, we got acquired by Micro Focus and Fortify. Some of you more enterprisey security guys may have heard of them. Working together, but still a standalone company, working together through Fortify and building out our products. So let's start off with how this cry wolf paradox affects your team. Maybe we heard about this paradox before. It's the boy that cried wolf, just for fun in the beginning to get the attention of his villagers. But the third time he cried wolf, when there was really a wolf there, no one came there to help him, and his sheep was eaten up by the wolf. This is the same principle with false alerts in your CI. And it turns out that this actually affects your companies quite severely. So about 70% experience alert fatigue from their security scanners today. And this can result in things such as employee turnover and create frictions between teams, between your SREs and security experts and the developers. Are you putting stones in their way that aren't really stones, that are just blockers for no reason? And in the end, you may miss critical security alerts that actually affect you, and this is due to the massive amount of false positives today. So when independent of the type of security tool they're using, just the subjective view on how many false positives are you experiencing, most of the security guys say that 25 to 75% of the security alerts are actually false positives in the end. This is a cat. It's not a wolf, but it's my cat, and it's actually named Wolf. But in Swedish, varg. Very Instagram-friendly name. We're going to talk about open source security to have some context here. The typical task here is software composition analysis, is where you scan your code to find out the libraries you have and map those to the vulnerabilities in those libraries and the specific versions you're using. And the thing is, you don't know the flaws you had a year ago. So it takes about 800 days for an open source software to find the vulnerable code and disclose a vulnerability. It's actually quite interesting. You probably heard about Log4Shell, the critical vulnerability in the Java logging library. The vulnerable code was there for 2,600 days without being found. It's also actually tricky to, when you know that you have a vulnerability, actually solving those. It takes about 100 days to to become up to date, or you're usually 100 days behind. And if you have a breach, it takes almost a year to actually fill the gap from that breach. And different communities are actually not performing the same in terms of finding the vulnerable code. We can see here a box chart where we can see that PyPy and NuGet are faster at finding the vulnerable code and disclosing vulnerabilities. While we can see that the giants, Maven and NPM, are a bit slower and have a median vulnerable code entry to vulnerability disclosure above 1,000 days. So Log4Shell was slow, but not that much slower than the median. So to reason about false positives in a security scanner, I typically talk about 4 things. Do you actually have the vulnerable package? So it's one thing that when there's a false positive, it might be that it's a match to the completely wrong package, or that it doesn't understand the version ranges, and you're not actually vulnerable to this because it's another version that is vulnerable and not yours. But then you also have the second layer, which is are you actually able to call the vulnerable code? From the production level, you should not be able to call your test dependencies that may have vulnerabilities, or build dependencies. Or you may know that a particular function in the open source project is vulnerable, and you're explicitly not trying to call it. And then we have, is it running in a critical environment, and is it exploitable? It's a thought framework. I contributed this to Linux Foundation a while back. And just to grasp the things we're going to talk about, in open source, we have some standards to work around in how we think about vulnerabilities. So we have a CVE, that is the actual vulnerability. It contains a summary of the flaw. It contains a link to some source, typically maybe a GitHub repository with a report, or maybe a blog post where someone has officially disclosed this. And these CVEs have unique identifiers and end up in databases where you can search for different vulnerabilities in different packages. Those are linked to CPEs. As you can see, there's a CPE string here. It's a unique identifier of a package. But this one is very, 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 very bad, actually, in my opinion, and I'm very opinionated about this. According to the CPE standard, it exists 50,000 packages, including different versions in the world. To my knowledge, it exists about 5 million packages, excluding versions, hundreds of millions if you include the versions as well. So CPE is far from complete. So therefore, 2 or 3 years ago, another standard emerged, which is the PURL. And this is typically what your package manager uses. So this is one-to-one compliant with NPM, with the Maven repository, and with PyPy and the pip CLI. And when you get different false positives, it may be because those things don't play along. You disclose vulnerabilities and link those to CPEs. But they are such a bad standard that it's actually hard to map that to the actual package that you're installing in your manifest files. And you get common weird false positives from this. So this inaccurate translation between these standards can be a thing such as here, where we can see on the CPE string here that it's the click project that is vulnerable. But there are actually 2 click projects. One which is very nice. It's a CLI generation framework in Python, and I use it a lot. I love it. And this one is a Ubuntu thing that you can use for different things. And it's clearly, as you can see, a click install.py thing that's vulnerable. Which one is it? It's actually this one. But it's very easy to think that it's this one. A typical false positive that we have tackled ourselves and can see that competitors are thinking about. And data can be stale in those different databases that handle the vulnerabilities as well. If we look at this new vulnerability in a NuGet package in the pipelines library, we can see that this CPE string should contain a version. But it doesn't. It just says that all versions of this library are always vulnerable forever. This is not the case, of course. If you go to the sources, you can see that they have specified in an issue clearly that there are version ranges, we just need better integrations to scrape that data, but also a common false positive in the first layer. Another false positive that we've seen are common are when there is ambiguity between the CLIs and SDKs of a library and the actual core itself. So for instance, here we have Elasticsearch. In the CPE string, we have Elasticsearch that is vulnerable. Is it the Docker image with the complete core of Elasticsearch, or is it the Python thing you install there? It's actually this one. But if the CPE string says it's the Python thing, it's the same CPE string. So this becomes quite tricky quite fast. A way to reason around this is there are two common metrics. You hear a security talk, but I'm actually a data scientist. So I frame this as a data science problem typically, and this is how I present this. You have two metrics here. We have precision and recall. Precision is the amount of true positives you find compared to the total things you find. In our benchmarks and in my belief where we need to be is that you should have no more than 2 to 5% false positives. So about every 20th, if it's more than every 20th vulnerability you get an alert for are false positives, you should review your options. And recall is actually trickier. You can't really know this. What is the total space of all vulnerabilities that you could potentially match to? There are no ground benchmarks for this out in the world yet. I think it's a prime thing that Linux Foundation should work on with OpenSSF. But this one is tricky. So my recommendation here is just do benchmark with different competitors depending on your setting of your application. And how we internally optimize our algorithms, if we have any other data scientists here, we know the F1 measure, it's a balance between precision and recall that you optimize for to reduce the number of false positives for your customer. But vulnerabilities today and false positives is not only about this. It's actually becoming more of an opinion. It's becoming deeper and deeper embedded into the application, and not only do I have a vulnerable package, but also am I able to being exploited and calling this vulnerable functionality in this package. And here we have another example, Jackson data binds or Jackson annotations. It's a serialization library, a commonly used one for Java, and everyone knows that uses this that there are some vulnerable functions here due to how it actually works. You can use them, but use them in a safe manner. Typical vulnerability you get a match on, but you're not actually vulnerable because people know that serialize your JSONs without letting them being executed and because it's a remote code execution vulnerability. So what the industry is trying to do, and no one, in my opinion, not even us, has truly achieved this yet, is to trying to see if you can call the vulnerable functionality. This means that you build call graphs and identify the vulnerable part of the open source project, not saying that the whole version is vulnerable, but only this little snippet of code is vulnerable. And seeing throughout your application, throughout all your dependencies, seeing if you can call that function. This is actually a fun task that I'm working on with my team to find this. And what you typically do is that you get the Git repository and the code from the distributed source, connect that to the vulnerability, see what has changed out through the different versions of that package. So here we can see that they actually patched older versions as well for this vulnerability. So we have different fixes in different minor versions. So what we do is that we build syntax trees from these. And we diff those syntax trees to see what has changed throughout the code and are able to determine which functions have changed. And we actually use some tricky machine learning here to see where we have fingerprints of what a typical vulnerability patch looks like to make this even more accurate. And then we get some information that this is the exact fingerprint function that is vulnerable. So it's the deserialization part of Jackson data binds that is actually vulnerable to this particular piece of vulnerability. And then matching that to your application, this is actually not that tricky. The tricky part is still there. So looking at the cat again, it's quite. We could open VS Code, Control F, see if we use the bean deserialization, and no results, save. Now, this is not actually the case. It's not a cat, it's a wolf this time. What you need to do is build a call graph. And a call graph is essentially a graph of what functions call what other functions, or methods, or classes. And this is very tricky to build. There is no way to build accurate, really accurate call graphs today. There's always a trade-off that you get a lot of false positives in the call graph, meaning that you get callees that you actually can't call, or that you miss calls in your call graph, and especially in dynamic languages. For instance, can you know what type a Python function actually returns? So great. We have reason about this. Now you have 30 scanners in your CI. Is this the way ahead? There is actually a battle here where we can say, now we talked a lot about the concept of false alerts and being able to deeply analyze your vulnerability if it actually is a false or true positive. But is this the way ahead? Is this what people are doing today? 40% of security professionals say that they lack actionability in their security alerts. And this is an ongoing discussion, and it's quite cool to look at the behavior in the open source community. Are they going for deep analysis and really understanding, are they vulnerable or not? Or are they just fixing it anyways by updating the libraries and propagating that throughout the dependency chain? And it turns out open source has picked remediation. It's faster, and it fixes the problem regardless of if it's a problem or not. So 65% of PRs that fix vulnerabilities and automatically generated PRs are merged, which has gone up, skyrocketed throughout the recent years. And by having this behavior, you also keep your dependencies more up to date, which makes you less susceptible to vulnerabilities that pop up. But you remember that it takes on a median of 800 days to find the vulnerable code for an open source project. So keeping things up to date is a good thing here. But there's concern with breaking changes, of course, when you update. And doing the update can be tricky as well, especially when targeting specific open source vulnerabilities. So, as you know, dependencies in open source is actually a tree, a large tree. I commonly see that in the NPM community, you have trees that are 40, 50 layers deep with vulnerabilities down there that you are vulnerable to, and you do get to call those vulnerabilities. It's tricky. And the NuGet is actually also a very deep language. And what it typically looks like is that you have vulnerabilities in your transitive dependencies. But how do we solve those in the transitive dependencies when we're in? We should, yeah. Let's dig deeper into that, because the actual depth of the vulnerable dependencies on average is the deepest in NPM, and NuGet is quite close behind in this sense. Now the graphs pan out at depth 9 here, but as I've said, I commonly find vulnerabilities when I help out customers on depth 40 for NPM. Maven is actually the least deep, and this is due to how they are able to resolve dependencies throughout the tree. I have another talk on that maps out all the different ways to resolve dependencies. It's very interesting. But what you want to do is, of course, update Lodash so that it becomes a safe version. But can we force update this transitive dependency? Sometimes you can. There is functionality in some package managers to do this. But in the end, with these breaking changes that people were worried about, you're isolating breaking changes between Lodash and some on core here. Is that where you want your breaking changes? Between an unknown and an unknown API? Probably not. You probably want your breaking changes at the root. So this can happen if with the breaking changes. This was a fun day for me as well. So it was a dependency in the cryptography library that is a transitive dependency, and they had a minor update that forced us to include Rust on the OS level. So this was a salty, fun comment here. I give it a thumbs up because I agree that that's not a minor update. And these breaking changes, as we've seen, can occur on the different levels. When things break, is quite interesting because there is the semver notation in these breaking changes. And, the minor patch. But if we look, and this statistics is actually only like one update. So from one patch to the closest next patch, 23% breaking changes. And there's no significant difference between the minor and major as well. And this is quite fun because this is Maven. It's a statically typed language. You know what functions, what type of function returns. And the most common things in Maven are actually that you do these like method removal, class removal, or change global variables in a way so that you break the tool chain. And of course, this is a static language. It should be easier to control breaking changes here. So what about Python? Well, it's actually also another tricky question. It's really hard to determine breaking changes in Python in this static manner. So when going through all the research, there were no conclusive data, only that it was much worse. Yeah. So of course, you don't want to handle that stuff down your dependency tree. You want to update at the root. But what root should you choose? Yeah, it's a graph problem. So we're going through all the different types of problems here. So this becomes a graph search problem on how to actually find these safe routes. I've done some research on that. Do we have any Neo4j people here? That's sad. I want to give them a compliment. They have a fantastic graph database. If you think it's fun to play with graphs, I can highly recommend it. They have a free version that's open source. So what I did is that I put, to be able to find the safe routes for transitive dependencies, we put all the open source and all the relations in one big graph database. And wrote graph search algorithms to be able to traverse these trees and reflect how each package manager actually resolves dependencies. Spoiler: Maven just picks the first one that occurs. And so, in the end, false positives. We deeply analyzing your security issues can sometimes be very daunting and a powerful there exist tools that are powerful enough to help you out with this, and that's great. But this costs time, and is this time you're willing to spend? And what is a false positive is very much becoming an opinion. Some people say that everything that doesn't go into production are false positives. But the JSON parser malware attack that I think it exfiltrated the all dot files from a computer, so SSH keys from your developers. If they install that on their private machines, is that a false positive? Even though that particular thing maybe not ended up in production, it's very much an opinion. So the open source community has chosen that powerful remediation is more valuable for them than deep analysis of their security vulnerabilities in open source. And I think that's an interesting thing. Like, it's not always of course, this is not always the thing you would recommend to a large enterprise that doesn't have the capability to keep dependencies up to date at that pace that you need to, as an open source, maybe be able to. But I think it's important to have the discussion: should we be able to fix, or should we be able to analyze? Because those are completely different skill sets that you may want to put that power to your security team, or put the fix power to your development teams. I should probably have had this slide up, but yeah. And that's it for me. I really enjoyed that that you wanted to come to my talk, and if you have any questions or differing opinions, I would love to hear them. Thank you very much.